Greetings, AP Chemistry students. This is Mr. Harper, and today we're going to talk about in this recording is we're briefly going to review some organic chemistry stuff. Now, whether you were in my class or Mafuchi's class last year, we talked about organic chemistry in my class fairly extensively about nomenclature and writing structures, that sort of thing of different compounds. And so today it's going to be kind of a review. What you need to take away from this is some basic tenets of naming and an awareness of the different organic functional groups and types of compounds. We're going to talk about these. You need to kind of commit some of these here to memory. I'm only showing you, there's a whole lot of different kinds of organic chemicals. I'm only showing you some of the ones that are most significant and looking into my crystal ball, the things that I foresee being on the AP exam. You do need to be able to identify these things in order to maximize your score. And so you may want to make some flashcards or something like that of the different functional groups so that you are able to do that effectively. Now, looking again into my crystal ball, I do not foresee having a question that is purely on organic chemistry, like a bunch of things about like organic reactions. That's just not going to be on there. But here is what is likely to be on there. You are almost certainly going to have to evaluate organic compounds in terms of intermolecular forces of attraction, or Lewis structures, or some kind of bonding, or in some other respect in which you're going to have to rationalize differences in the behavior of different chemicals based on their structure. Okay? That is most definitely going to be there. Now, that's all stuff you guys know, but you need to think about what it is that you need to review most, and then go review those things, because, of course, the AP exam is here in just a couple of days. So first, some prefixes, okay? Organic chemistry is the chemistry of carbon, basically, right? Or organic means carbon-based in chemistry, right? And so we have these different prefixes that mean different numbers of carbons in a carbon chain. So, of course, as you guys remember, meth is 1, eth is 2, prop is 3, bute is 4, pent is 5, hex is 6, hept is 7, oct is 8, non is 9, dec is 10. You're most likely to see things in this range, but not necessarily. Oftentimes, things that have a carbon chain longer than 10 carbons are known by some other name other than their systematic name, because it gets to be too crazy. So, for example, if you look at a name and you see that it is, well, butane, well, butane, of course, is the fuel in lighters, but butane, the name, the way this is put together, tells me that bute means we got 4 carbons, ane, the suffix, means that it's an alkane having all single bonds, and so the name is indicative of the structure. You got to know those prefixes, okay? Now, your first and most simple kind of organic chemical is called an alkane, okay? And alkanes are known as saturated hydrocarbons, okay? What that saturation means, what saturated means here as an adjective, means that the carbon atoms have as many bonds, or bonds to as many different bonding partners as they can have, okay, as they have entirely single bonds, and the generic formula is N carbons and then 2N plus 2 hydrogens. So we got a couple of these drawn right here. This one is what would be called a straight chain alkane, because the carbons are aligned here in a chain. Now, remember that really it's not going to have this flat kind of geometry here, okay? And then because I'm too lazy to draw a bunch of hydrogens, I just have lines drawn to the carbon. Understand, if I have nothing else for this podcast, guys, understand that if I have nothing attached to the end of that bond, that means that there's going to be a hydrogen there in its place. I'm just too lazy to draw them all. It would take me the rest of my life, okay? Now, if I named this guy, this would be just what we talked about before. That would be named butane, okay? Alkanes, you can identify an alkane because they end in ane. That is the suffix. That means it has all single bonds. Now, this guy here could also be called N-butane, N standing for normal or unbranched. The formula of this compound would be 4 carbons, okay, so C4, and then if you count it up, H10. Now, here's why this N is important. Down here, you guys can also see, if you count this up, this baby here has got 1, 2, 3, 4 carbons, and it also has got 10 hydrogens. And so these guys right there, that's going to be the structure, or the formula of this guy right there. These guys right here, because they have the same formula and different structures, are called isomers. Because they have similar structures and similar composition and similar molar mass, you would expect they're going to behave in a similar fashion, but not exactly the same. They will have different boiling points and etc. because they have different shapes. You would in fact expect that this guy right here, the one on the bottom, would have a lower boiling point because there's less opportunity for this guy to interact with other molecules of the same type. This guy here is going to, because it is more spread out, has a greater surface area, and is going to have more contact with other molecules, and therefore stronger intermolecular forces between the molecules. For both these guys, you guys should realize that they are going to be non-polar, and your strongest kind of intermolecular forces of attraction are going to be London dispersion forces. Now, please, guys, on the AP exam, do not abbreviate London dispersion forces, LDF. I'm doing that because I can. I have a degree in chemistry. Until you, too, have a degree in chemistry, you cannot abbreviate in your responses. Okay, so this guy down here has the same form as C4H10. It is an isomer, okay, as is N-butane. Okay, now this is what we would call a branched hydrocarbon because we have one chain that is the longest, 3 carbons in length, and then we have this other side, carbon over here, essentially replacing a hydrogen, okay, in that area. So this guy, because the longest chain is 3, would be called a propane, okay. This branch right here is 1 carbon long, and so we would call that baby a methylpropane. And if we wanted to be really complete, we'd say 2-methylpropane because that methyl side chain is attached to the second carbon in the long chain. Okay? Now again, on the AP exam, they're not going to I would bet money they're not going to ask you, name these compounds, okay? But they might have some question that goes along with, drawing isomers or identifying these two are isomers and rationalizing differences in properties and that sort of thing. So you should be aware of those things. Now, a couple other things to talk about, okay? I'm going to turn to red here. If I look here at this structure, understand this is not really the 3-dimensional shape of this molecule. As you guys may remember, if I look here at this carbon atom, okay, and I look at the geometry around that carbon atom, this carbon is going to have a tetrahedral arrangement of electron pairs because it has 4 bonds to that carbon. You'll also remember that this carbon here is sp3 hybridized, okay? And so if I look, sp3 hybridized, okay, and of course, this is bonded to the other carbons and to the hydrogens through sigma bonds. That's what these single bonds here are called. They're called sigma bonds due to the shape of the bond, the way the orbitals overlap and stuff, okay? Due to the tetrahedral geometry around that carbon atom, really this bond angle is something like 109.5 degrees, as are all these other bond angles over here. And so really this in 3 dimensions is going to look sort of like zigzaggy, or, well, not that many zags, but, you guys get the idea, okay? Now, along kind of with this whole topic of alkanes is something called line notation. As you guys saw, it's pretty difficult. Well, not difficult, but it takes time to write the structure of butane, even if I neglect the hydrogens, and chemists are a lazy bunch. So we might also represent this molecule this way, like line, 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 like that, okay? And here's what this means. It's implied that there's a carbon at each end and each vertex. So here there'd be a carbon and a carbon and a carbon and a carbon. Okay, I'm filling the blanks for you, but really this is the same thing. Really this is the line notation for butane. Okay, and then attached to each carbon is going to be as many hydrogens as it can possibly hold. So right here I'm going to have 3. Right here I'm going to have 2. Here I'll have 2, and here I'll have 3. And this is the same thing as this, okay? But that's more kind of close to its real shape than this is right here. And so I can do that for any, length of alkane or any other organic compound, okay? Now, of course, something small like that, it just looks goofy, right? Because we're going to have 3 carbons, 1, 2, 3 carbons, and, whatever. But, the bigger the molecule is, the more convenient line notation becomes. So if we look at something like 1, 2, 3, 4... 5, 6, 7, 8 carbons, which this baby would be called octane, right? Well, it's an awful lot of work to write out all these carbons and hydrogens and whatever. So I do it like this: 1, 2, 3, 4, 5, 6, 7, 8, and there's my. I'll draw it neater than me, guys, but there would be my line notation structure for that compound. So there you go. That's how that works. Okay. Now, kind of along with alkanes, we also have things called cyclic alkanes, and the difference between these guys and a straight alkane is that instead of the carbons being in a line, here they're in kind of a ring structure. Now, if I count this baby up, its formula looks like this. It's going to be C3H6, okay? These all have the generic formula N carbons and 2N hydrogens. If I wanted to name this guy, there's 3 carbons in the chain, so we would be tempted to call that baby propane. But to avoid confusion with the straight alkane, we call these cyclopropane, because it means the carbons are attached in a ring. In the same way, this guy here would be called cyclopentane. And this guy here, if we count it up, how many carbons, guys? It has got 1, 2, 3, 4, 5, 6. This is a line notation for cyclohexane, whatever. Okay? Also related to what we just talked about. Okay, so the both things, alkanes and cycloalkanes, are hydrocarbons. These right here are also hydrocarbons, meaning that they are just composed of carbon and hydrogen. However, alkenes are not saturated. These are called unsaturated hydrocarbons. Kind of like when you talk about unsaturated fats. That's what this actually means. It refers to the bonding. Okay? An alkene has at least one double bond as part of the formula. And so you can see here that each carbon is not bonded to as many different atoms as it could possibly bond to. And so that's why it's called unsaturated. Okay? So if we look here at this guy right here, and by the way you name these that is different from an alkane is instead of ending in ane, they end in ene to signify they have a double bond. So this guy here, we got 2 carbons, so the prefix is eth, and the ending is ene. So this is ethene. Okay? This guy right here would be called butene. It's got 4 carbons and a double bond. And this guy here, if you look at it, is also got 4 carbons, so it's going to be a bute, and then end in ene. Now notice, if you take a look here at these second 2 structures, this one and this one down here, they're the same except for the location of the double bond. Now that double bond difference does give them a difference in properties, and so we have to find a way to specify that. And the way that's done is with a number. This is called 1-butane, this is called 2-butene. Here's why. If I number the main carbon chain, 1, 2, 3, and 4, the double bond starts on carbon 1 here, and so I call that 1-butene. Here it starts on carbon 2, and so I call this baby 2-butene, because that's where that double bond starts. Like before, we can see these guys here have the same formula, but different structures. These are also isomers of each other. Okay, same formula, different structure. Okay, that's what an alkene is. Now, whereas alkanes are very unreactive, okay, alkenes do have some important reactions they can go through, but you don't have to know that for the AP exam. Mainly, like hydrocarbons, just kind of get burned. They're used for fuels. Also, like alkanes, these are non-polar molecules, comparatively speaking. I mean, when I say they're non-polar, everything in reality has a dipole moment, but for a lot of things it's pretty small. For hydrocarbons of pretty much any kind, a pure hydrocarbon is going to be fairly non-polar, right? They're going to exhibit weaker London dispersion forces of attraction between them, okay? And so, as the molecules get bigger, the strength of those attractive forces increase. But again, if I'm comparing them to something else that's more polar, they will be fairly weak. Okay, last type of hydrocarbon, well, second to last type of hydrocarbon you guys have to talk about are called alkynes, okay? These are, again, things we describe as being unsaturated, okay? And the defining characteristic of an alkyne is that it has at least one triple bond as part of the formula. To signify they have a triple bond, these end in Y and E when they are named. So this guy right here has got 3 carbons, prefix would be prop, ending would be ine. This guy right here has got 1, 2, 3, 4, 5 carbons, so the prefix would be pent, and the ending would be ine. Okay? Now, also, you guys can see, there's more than one place we could put that triple bond. So because of that, we have to specify where it is at. So this starts, as you can see on the second carbon of the chain, we call that baby 2, pent-ine. Okay, for the sake of argument. Okay, naming-wise. Now, let's talk about another important group of organic compounds. So far we've looked just at hydrocarbons, made just of carbon and hydrogen. Those are like your basic kinds of organic molecules, okay? We're going to go now and look at other kinds, and the way that other kinds of organic compounds are formed, you can kind of think, is kind of like if I took a hydrogen on a hydrocarbon and replaced it with something else. If I took that hydrogen away and then put something else in its place, that's how we would get these other kinds of organic compounds, okay? The first one we're going to look at are called alcohols, which you guys are familiar with. What defines an alcohol is that they contain this functional group, OH, okay, which really looks like this. It's got OH like that, and the 2 lone pairs of electrons right there. This is called the hydroxyl functional group. It has a name, okay? Now, this guy right here, okay, is a simple one. Okay, this is kind of very similar, if you look at it structurally, to this hydrocarbon right here, which is called ethane, right? Now, you can kind of think that if I take this guy and I were to chop off that hydrogen and replace it with the OH, that would give me this alcohol right there. So when I name this guy, here's how it goes. I'm going to start with the name of the parent hydrocarbon, which is ethane. I'm going to take off the E, and I'm going to add a suffix that tells me it is an alcohol. The suffix here is OL, and so the name of this compound here is ethanol. Okay? In the same way, you guys can see that this guy right here has got 3 carbons in the chain, and so you can think that this was derived from propane. So we'd call this baby propanol. And this guy here has got 3 carbons in the chain and the hydroxyl group there, so we'd also call this baby here a propanol. However, as we've seen before, I'm showing you guys this a bunch of times so you guys get the message. These guys right here have got the same formulas, but different structures. Okay, this guy's got the hydroxyl group on the end carbon. This one has it on the middle carbon. So if I number this chain, 1, 2, 3, here the hydroxyl group's on the end carbon, so I'd call it maybe 1 propanol. Here it's on the middle carbon, I'd call it maybe 2 propanol, because if I number the chain, there we go. Okay, these guys again are going to be isomers of each other. This one right here is also referred to sometimes as isopropyl alcohol. That's what's used to clean with in your house, that sort of thing. Here, this is not used really for much anything around your house. Okay. Now, if you think about alcohols, here's something they've all have got in common. You guys see they've got this OH functional group here. Well, just like water has that polar oxygen-hydrogen bond, which leads to a partial positive charge here and a partial negative charge here, these guys have all got that because of that OH functional group. Okay? Now, that means that when you dissolve, or when these guys are together, or when they're dissolved in water, they're able to form strong hydrogen bond type attractions to each other. So if I compare an alcohol to, say, an alkane of similar size, if I were to compare the boiling points of ethanol and ethane, the boiling point of ethanol is gigantically higher than that of ethane, because here this has got that OH functional group. It can form hydrogen bonds to other ethanol molecules. The ethane here cannot do that because this bond is not real polar. These guys are just attracted to each other through weaker London dispersion forces types of attraction. That's the kind of question you have to be prepared to address on the AP exams. You need to know your intermolecular forces and need to be able to correlate structure to the function. Also, just some trivia for you guys. If you look here at the hybridization of all these things, here the carbon again is sp3 hybridized. Here that oxygen is also going to be sp3 hybridized. So if we looked at bond angles and stuff, well, we'd say that bond angle would be around 109.5 degrees. And this one here, even though we're drawn as being straight, is likewise going to be in the area of something like 109.5 degrees. But you're going to remember that, of course, that really is going to be less than 109.5 degrees, because although the oxygen here has a tetrahedral electron pair geometry around it, the presence of the lone pair electrons distorts the bond angle, is going to squish these guys closer together than they would be otherwise, and so that's why your bond angle is less than 109.5 degrees. If I look here at this molecule, all the bonds in it are sigma bonds, because they're all single and result from the end-on-end overlap of orbitals. Okay? There you guys go. Some information for you. Okay, other stuff. Oh, yeah, okay, let me go back, actually. Now, here, I wanted to spell a couple things really quick, okay? 2 things that will break my heart and kill me to death if you guys write them on the AP exam. When you guys look at all organic compounds, unless I tell you otherwise, like this guy right here, okay, these do not dissociate. This is one of the most common things people say incorrectly on the AP exam. Alcohols do not dissociate in water. People see this OH, sometimes they think, oh, it's a base because it has OH in there. This is not a hydroxide ion. This is attached by a covalent bond to the carbon, so this is not going to pop off. In a similar fashion, these do not donate protons. These are not acids of any appreciable strength, so don't say that. When these guys dissolve in water, they remain intact, okay, and they disperse through the water, and they're attracted to water through hydrogen bonding because of the polar OH group, okay? So these do not dissociate, nor do any other organic compounds unless I tell you otherwise. Okay, now let's look at something else. Amines are another important thing. Okay, amines all have got an NH2 functional group as part of the molecule. So if you look at this guy right here, this is an amine with 2 carbons here. You can kind of think of that the parent of this molecule was, again, ethane, my 2-carbon alkane. The difference being, to go from this to this up here, if I take off that hydrogen and add NH2 onto the side, okay? That's how I go from there to there. Now, because of that, I name this molecule just like I name ethane. I'm going to say ethane, and then I'm going to take off that E, and I'm going to add a suffix. Amines tend to be named ending with this suffix right there, amine. So if I put that together, this would be called ethanamine right here, okay? This guy right here has got a 3-carbon chain, so I'd call that propanamine. And I'd say it's going to be 2-propanamine because my functional group, okay, this group, by the way, functional group means a group of atoms responsible for the behavior of that substance. All amines have got this group of atoms there that gives them their properties, okay? So this is ethanamine, 2-propanamine, whatever. Now, something you guys want to know about amines, okay? You need to recognize that amines are weak bases. They will all accept a proton. Okay, and the reason for that is, of course, because they've got this nitrogen with the lone pair of electrons. That makes, this is where an H plus ion is going to get attached right there, where these electrons are going to form a bond and accept the H plus, and it'll form then the conjugate acid of the amine. So these guys are weak bases. When you put them in water, they can all react with water. Like if I think about here, ethylamine. Ethylamine, if I just draw its structure, whatever, NH2, okay, this guy, if I dissolve into water, will react with water, and when that happens, the process is reversible, and we're going to make this guy right here, okay, and then plus hydroxide ions. This, of course, is positive. This would be called the ethyl ammonium. Oh, brother, I can't spell. Ion, whatever, okay, but this is the conjugate acid of that guy, okay? Now, to confuse you, this is the systematic name for ethanamine. Sometimes this might also be called ethylamine. That's a common name, not a systematic name. Doesn't matter. I just want you guys to understand, if you guys see that, it's referring to this compound right there, okay? Aldehydes, okay, something else. This may show up in the multiple choice. I don't anticipate there being a large response about it, but just in case, okay? An aldehyde has got this functional group in it. You see, it's got the carbon, double bond to oxygen, and then it's got a hydrogen on this side, and then over here it says R. And you say, Mr. Harper, there's no element R on the periodic table. What are you talking about? Okay? Anytime you guys see an R as part of the structure, that is like a generic carbon chain. Okay? So it could be of any length. Basically, this is saying that the other part of my molecule is a carbon chain. If on the end of the carbon chain I've got this functional group, it classifies as an aldehyde. And when you name these guys, the suffix is al, okay? Now, this one right here, okay, is, you can kind of think we got the 1 carbon, so it's derived from methane. So we'd call that baby meth and al. Now, you probably have already heard of this compound right here. The trade name of this substance is formaldehyde. Yeah, okay? This guy here in a similar fashion would be called ethanal. This guy here would be called propanal. Now, a couple things I'd like to point out to you guys about aldehydes. If we think about the bonding that is present in here, okay? This carbon, if we look at it, is not sp3 hybridized. It is sp2 hybridized. And what that means is that the geometry around this carbon atom right here is going to be trigonal planar. And so this bond angle and this bond angle and this bond angle here is going to be something in the vicinity of 120 degrees. If I look at these bonds right here, that's a sigma bond, that's a sigma bond, and then right here, okay, they've got this double bond between the carbon and oxygen. That's going to consist of a sigma bond and a pi bond coming from the overlap of unhybridized p orbitals in both the carbon and the oxygen. This guy here is also going to be sp2 hybridized, incidentally, okay? Now, there you go. Now, something else you guys are going to want to take note of here about this molecule, because oxygen has a high electronegativity, this molecule is going to be moderately polar. And if we look at the dipole, this end down here would be the positive end, and the negative would be up there. And so if I compare, for example, methanol and methane, you would expect methanol would have the higher boiling point or stronger intermolecular forces because this is a polar molecule and is going to exhibit a significant dipole because of its structure. And these guys here follow suit. Because they've got that functional group there, these molecules are somewhat polar and will have higher boiling points than the corresponding hydrocarbons or whatever. Okay? A similar kind of compound are called ketones. The difference here being that in a ketone, you still have the carbon double bond to oxygen, but it's in between two different carbon chains. So, for example, if you look down here at this guy right here, you see we've got that functional group here in between two different carbons. Now, when we name this, we look at the longest carbon chain, which is 3, and so it's kind of like propane, right? But we take off the E, and we're going to slap on the appropriate suffix. Here, the suffix is "one," O-N-E, so this is called propanone. This guy here, we would call pentanone. This guy here, we would also call pentanone because it's got the 5-carbon chain, and then the carbonyl group there somewhere not on the end. The difference here would be we'd call this 2 pentanones, since that's on the 2nd carbon. We'd call this one here 3 pentanones, since this is on the 3rd carbon. In the same way that we talked about here for the aldehydes, like we look here at propanone, you can also tell that if we look here at this carbon, that's going to be sp2 hybridized, and so really this is going to be a trigonal planar electron pair geometry. And so although we're drawing this as being straight, really this bond angle here is more like 120 degrees. And so this is again going to be a somewhat polar molecule where the negative end of the dipole is up here because oxygen's got that high electronegativity, and then the positive end is going to be down here by the carbons. Okay? Those are what ketones are. Okay? Another very significant one are carboxylic acids. Okay? Now remember I told you guys that organic compounds do not dissociate in water when they get dissolved. This is the exception. Carboxylic acids do dissociate. Okay? They do break apart to a small degree to yield ions in water. These are almost universally going to be weak acids, and the exceptions to that statement you do not have to worry about for the AP exam. Okay, so just a few of these right here. Okay, all carboxylic acids have this functional group, which you should all be intimately familiar with. Okay, but if you are not, you need to commit it to memory. Anytime you guys see the carbon double bond to oxygen, single bond oxygen, hydrogen right there, okay, that tells you that that is going to be an acid, where this is the acidic hydrogen in each case. Okay, if I look at these, okay, I just want to name a couple of these real quick. Okay, this guy here is called methanoic acid. Okay, also called by the trade name formic acid, which I think I told you guys about. This guy here is called ethanoic acid, okay, also known as acetic acid. And then over here, because this guy's got 3 carbons in the chain, we call that baby propanoic acid, okay? And so a couple of important things, okay? Of course, you guys remember that this is the acidic hydrogen in each case, okay? Also remember these guys are weak acids. When I take this guy right here, if I were to react that baby with water, okay, it would establish equilibrium. We would form a small amount of hydronium ions, and then we would have the conjugate base, CH3CO2 minus, which is called the acetate, or you could also call that ethNO8 ion. Okay, that forms. Now, something that's kind of interesting here is if you guys take a look here at that carbon, that baby there is sp2 hybridized. If you look in this structure at this bond and this bond, they're definitely different. This is a double bond, this is a single bond. If you look at the structure of the acetate ion, though, okay, here we get carbon, hydrogen, 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 and then carbon, double bond, oxygen, okay, and then single bond oxygen, like that. Here's something that's kind of interesting, guys, is that really I'm drawing this here as being, you know, double bond here, single bond here, but really, if you guys recall, this double bond gets shared between both the carbon-oxygen bonds, okay, through, you can either describe it as being resonance, or because of the fact that Each of the oxygens and the carbon is sp2 hybridized and share the pi bond electrons right here as part of one of those delocalized pi bond sort of things where the electrons get shared. Okay. If you have questions about those things, you'll want to talk to me about that here in the next couple of days. Okay, but just throwing that out there so in case you guys remembered. Okay. Last one here second to last one I want to talk about here are ethers. Okay. By the way, if you look back at carboxylic acids here for a second, if you think about intermolecular forces, strongest type these guys can exhibit is hydrogen bonding. These, again, are going to have comparatively high boiling points compared to other kinds of organic molecules because of the strong attractive forces between the separate molecules. Also, these form strong interactions with water, which is why they are so soluble in water. Okay? Last one here, ethers. Now, here's something you guys need to know. Ethers are a great example of something that is comparatively nonpolar. Because they're nonpolar, the AP test uses these a lot as examples of things that are going to have very low boiling points. Because they're comparatively nonpolar, the most significant type of attractive force between ether molecules is London dispersion. Okay? Forces. Okay, here's the generic structure of an ether. You have an oxygen connecting two carbon chains. Okay? Now, because this is, oftentimes is fairly symmetrical, that's one way you can sort of rationalize, well, these are not particularly polar. Okay? Now, if you think actually about the shape of these, the shape's a little bit deceiving. If you look at the shape, right, really, this is an sp3 hybridized oxygen, so the shape would be something like this, in fact, where we have my lone pair of electrons up there. So you would, in fact, if you expect to see a very tiny dipole in this molecule, but not really that major. Okay? If we take a look here at a couple, this guy right here is called dimethyl ether. Okay? Over here, this guy right here, we have, and the reason it's called dimethyl, di stands for 2. Each of the carbon branches is 1 carbon long. Okay, so that's why it's called dimethyl. And then over here, if you look, each carbon chain has got 2 carbons, and so this is called diethyl. Okay, ether. Okay, now ethers a lot of times are used as solvents. Okay, for different organic reactions because they're comparatively nonpolar. They don't mix with water well. Okay, and also they have low boiling points, so they're easily evaporated after the reaction is complete. Now, both of these, if you look at them that I showed you guys, dimethyl and diethyl ether, are symmetrical. They don't have to be that way. You could have something where we have like a 2 carbon branch and then oxygen, okay, and then a carbon over here, okay, and it would look sort of like that. We would call that maybe ethyl, methyl, ether. Again, you guys don't have to really concern yourself too hard with that stuff. You're not going to probably have to name these on the test. I just want you guys to be aware of the various different kinds of organic chemicals and their general properties. I think that's the last slide. Okay, now we're going to continue recording, and we're going to go back here for just a second. We want to add one more thing that occurred to me. Okay, we're going to go to a white screen. I want really quickly here to remind you guys about some things called aromatic compounds. Okay? Aromatic compounds are things that contain benzene. Okay? Aromatic means smelly. It turns out that a lot of benzene-based compounds are pretty smelly. Now, benzene is this molecule right here. This is one that you guys should write down. This is benzene. We have carbon, bond to carbon, bond to carbon, bond to carbon, 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 and carbon. I am miserable at drawing this structure. Okay? And then bond to hydrogen, bond hydrogen, bond hydrogen, bond hydrogen, bond hydrogen, bond hydrogen. Okay? This is often commonly written like this. Okay, for the sake of ease. So we got line, 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 like that. Okay, it's got 3 double bonds. Now, we've used this as an example before of something that exhibits resonance because really that's not the only way I can arrange the double bonds. I can also have them between the other carbons. Okay? Bond, 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 like that. Now, in reality, neither one of these 2 Lewis structures that I just wrote up here on the screen are the way that it exists. It really exists as a hybrid of these 2 structures because these pi bond, if you guys look, there's 3 pi bonds, right? Those I guess you could say 6 pi bond electrons are not localized. They're shared amongst all the carbon atoms because each of these carbon atoms here are all sp2 hybridized. And so if you look here at this molecule, it is flat, it is planar, my bond angles are all 120 degrees, etc. Okay? Now, some things you guys ought to know about benzene, besides the fact that it's one of those things that exhibits resonance, is that it is unusually stable. It turns out that when you have this special number here of pi bond electrons and the alternating double single sort of structural motif that it makes for a very stable molecule, you probably don't have to know that for the AP exam, but just some trivia for you guys. Ladies and gentlemen, that is all we've got, okay, for today. And I hope you guys have a good night, and we will talk some more about this probably tomorrow. Hasta la vista.